Welcome to Statistical Computing with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be covering the second half of data visualization, focusing on producing beautiful plots in R using the grammar of graphics. So I'll scroll down from the top of the website down to data visualization, and I'll have a slide right here. That's the one we'll be looking at, part 2. So of the slide deck, this is slide 36 of 65 in this iteration. Plotting with ggplot 2. So you'll first need to install this package. That can be done with this command, install.packages, and it will install its dependencies as well. And each time you use it, within an R session, you'll need to load the library by using library ggplot2. Now, ggplot2 includes a dataset called MPG. That's for miles per gallon. And if you do $MPG, we'll get help on that. So let's go over to R, and I will library ggplot2. And before I press enter, I'm going to go over to packages, just show you what happens when you run library. I have a lot of packages, so that takes a little while. So I'll scroll down to ggplot. Here we are, an implementation of the grammar of graphics. When I press enter in the console window, I'll get a check mark right here. So I'll press enter, and there's my check mark. So that indicates that the package is loaded. All right, let me expand the help window, and I'll do $MPG for miles per gallon. This is the fuel economy data from 1999 to 2008 for 38 popular models of car. The data is from the EPA, that's the Environmental Protection Agency, and the data is available on fueleconomy.gov. The variables are listed here. We've got the manufacturer, the model, the displacement, that is how large it is in liters. So if you were to submerge the engine of the car in water, this would be the volume of the engine. Please don't do that to your engines. The year it's made, the number of cylinders the car has, the type of transmission, whether it's an automatic or standard, drive, whether it's front-wheel drive, rear-wheel drive, or four-wheel drive. Then we've got miles per gallon in the city and on the highway. And then we have two others, FL and class, which I don't know what they are, and we're not going to bother looking at them. If we look at the head of this data set, it gives us the first 6 rows. And I always prefer looking at the structure. str gives us the structure. Whenever I first encounter an object in R, I almost always first look at the structure of that object to see whether it's a data frame, a matrix, a list, a vector. Who knows what it could be? I just want to know. And structure tells me. So here I get the structure and tells me that this is a data frame. Has 234 observations and 11 variables. And the 11 variables are listed here. Okay. It tells me for each variable whether it is what the data type is. So this first variable is a factor variable. It has 15 levels, and the first couple are Audi and Chevrolet. The ones indicate that the first several of these are Audi. We'll get other numbers, 2, 3, 4, and so on, up to 15, which each correspond or are an indicator for what label they have, Audi, Chevrolet, and so on. That's the same for model. Displacement is a number. So the first several values in this data frame are 1.8, 1.8, 2.2, 2.8, and so on. Year is an integer. That's a type of number, but it just doesn't have a decimal. Cylinders is an integer, factor, integer, factor. Okay. If we ask for the summary of a data frame, for each column, depending on the data type, it will provide us a form of summary for that variable. So for example, manufacturer was a factor variable, and so it's going to give us a frequency table. It says that for the manufacturer Dodge, there were 37 instances in the data frame. And notice the frequencies are in descending order. So we have the most frequent at the top, and it decreases. Now I get 7 categories here, the last one being all the other ones combined, 74 of those. For displacement, that was a numeric variable, and we get the 5-number summary, the minimum, the first quartile, the median, the third quartile, and the maximum. Those are the numbers that divide the data set into equal quarters between each of those pairs of numbers. And we also have the mean, which gives us some information about whether the data is symmetric or not. If the mean and the median are close to each other, that indicates symmetry. By the way, that closeness, of course, depends on the spread of the data. All right, here's our first instance of ggplot. Now, the grammar of graphics specifies, and I'm going to give you a very descriptive definition of these terms. Grammar of graphics does things in layers by encoding variables to different, in what Hadley Wickham calls aesthetics, or meaning things like shape, color, size, location along an axis. These are all ways of encoding information. So the ggplot function is the first thing you need to run. MPG is the data set, and we are going to assign 2 aesthetics. We are first going to encode the displacement of the engine as the distance along the x-axis. So that's going to be this horizontal axis down here. It's labeled displacement. Y, we're going to encode the highway miles per gallon. We're going to encode that along a position of the y-axis. That's this axis here. And I'm going to assign that to P for plot. So we have our initial encodings of just the x-axis and the y-axis. We haven't told ggplot what to actually plot yet, but we've set up the axes. Now we're going to add a layer, and that layer has a certain geometric object. For every observation in the data set, we are going to add a point. Okay, so the geometric object, or the geome, is going to be a point. And we're going to take the original P, which we got from ggplot, and we're going to add to that a layer of points. And we're going to update P. So this P now has the original axes as well as the points in it. We ask to print that plot, and we get what you see. X-axis is displacement, y-axis is highway miles, and we have dots for every observation. This structure will allow us to add layer upon layer upon layer upon layer, so that we can plot the data, we can plot summaries of the data, and so on. So, the geome is the type of plot. We saw the points before. We have aesthetics. Those are types of encodings. And, for example, shape, color, size. Alpha is opacity, sort of the inverse of, or 1 minus transparency. It tells you whether you can see through an object or not. And then facets are small multiples. And so we'll look at all of those things shortly. There's lots of help for this, and I am regularly going to the internet and typing r space ggplot space my question. And Stack Exchange and many other websites are very helpful there. I think the help manuals are also pretty good. So let's add an aesthetic. So to the previous plot, all we've added is this one component. Within the points, we're adding an aesthetic to the points. We are assigning or encoding class as the color. And you see now we've got colored points, and automatically we have a legend on the right. And for each color, we have the label. These colors are picked so that they are roughly uniformly spaced within hue space. So if you think of a color wheel, they're roughly equally spaced within that color wheel. It's very tricky to choose good colors, and there is a website called Color Brewer, which helps with palettes, color palettes. All right, I recommend experimenting. Okay, we're going to see some experimentation in a moment. You know, assign different variables to aesthetics of color, size, shape, and look at the help and see what other aesthetics are available. You know, see what the difference is whether you assign a discrete to a color versus a continuous variable to a color. You'll get different behavior. And what happens when you combine multiple aesthetics? So, just to give you a sense of what the behavior is that you should expect, we have got aesthetics here down the first column of color, size, and shape, and the columns are labeled for discrete variables and for continuous variables. So for example, color, you'll get a rainbow of colors, just like we saw in the previous slide. For a continuous variable, you'll get a gradient from red to blue. And you have complete control over what the exact mapping of these gradients or rainbow of colors are. And the defaults are, I believe, well chosen. Size, you'll get discrete size steps for a discrete variable, and you can choose what the minimum size and the maximum size is for that range. For a continuous variable, you'll get a nice continuous mapping between radius and the value. Now you have to be aware that when you map to radius, if you see a circle, your eye sees an area which is scaling much faster than the radius is. So be aware of limitations of some of these mappings. And finally, for the shape, you'll get a different shape for each when you get a discrete, and you know, it's hard to know what to do if you're trying to map a continuous variable to shape. Really, that shouldn't work. So here I've gone and added 3 aesthetics for these points. The class of the vehicle I've mapped to color, so we've got that legend here. So we see the different colors just as we saw before. Now I've added the cylinder, the number of cylinders, to size, and you can see from small to large that legend here. So we have small engines on the left, which have very little displacement, and then as you increase the cylinder size, that is the size of the points, the displacement gets larger. That makes sense to me. Drive is the whether it's four-wheel drive, front-wheel drive, or rear-wheel drive, that's mapped to shape. So here are the 3 shapes. It's a circle, triangle, and square. And so you can see all these squares right here, these big squares, are rear-wheel drives, 8 cylinders because they're the big points, and it's a 2-seater. All right, those are your midlife crisis hot rod vehicles up here. And then you've got your sensible, all these points are like front-wheel drive, 4-cylinder. It's hard to see what color they are. They're going to be like minivans and stuff. We got purples. There's a purple point. There's sort of a gold brown color. It's this color here. That color is a compact car. Okay, and midsize or minivan, I forget now. So, all right. So, here's an instance of adding alpha. So alpha is opacity, and 1/4 means that it effectively takes 4 points to lie on top of each other before you get an opaque color. So if I flip back and forth between the previous slide and this slide, you can see the overlap. In particular, there is a circle on top of a square right here, which you could see here, but it's hard to see that square. Okay? If I go forward, they basically have equal weight in their visual. This purple dot down here, it looked like one dot before, and if I go forward, it looks sort of bluish now. So maybe there were two blue points and a pink point, and the pink one laid on top. So transparency or opacity can help reveal whether points are laying on top of each other. I think that 1/4 is too transparent. Okay, maybe 1/2 would be slightly better, but that's a parameter you can play with. Alpha can also be mapped to or a variable can be mapped to alpha. Okay, notice I've put alpha outside of the aesthetic command because I'm not mapping a variable to it. So facets. We've seen facets in the previous lecture. It's using small multiples to display different subsets of the data. It's very useful to explore large data sets over continuous variables especially, and for making comparisons. So we have a number of ways to facet in ggplot, and what I'm going to do here is show you 4 ways. Here is a ggplot. Okay, we're doing the same plot that we did before, displacement and highway miles, and to that I'm adding geom points. This is effectively the very first plot we did. That's P. Now I'm creating 4 other objects, P1, P2, all the way down to P4, okay? And each one is this original scatter plot, just to remind us what that original scatter plot was. That's this scatter plot here. So I'll run back. The first 3 are all using the command facet grid. So facet grid is going to give us a grid, rows and columns, that we facet by. And the rows are specified as the first argument, then we have a tilde, and then we have another variable which specifies the columns. So the first one we're going to have columns for the different cylinder types. The second one we will have rows for the drive type, and the third one will have drive, rows, and cylinder columns. Finally, facet wrap will simply lay out a plot along a row, and then until it hits the right margin, and go to the next line and go to the next line until it plots all the classes. That's a good case. So class here there's 7 different classes. When you have a large number of categorical variables, facet wrap is a handy one. And notice that there's nothing before the tilde. Up here, notice that there was a period before the tilde as a placeholder for either the row or the column. And then we'll print each one. So if we print P1, first one, okay, here's our facet grid. We see that we have the rows are dot, so that means there's no faceting, tilde cylinder. So we've got 4 cylinder, 5 cylinder. Believe it or not, there are a few vehicles that have 5 cylinders in them, 6 and 8. Let's go to the next plot. Now this is the drive type. Notice we've got rows. So we have 4-wheel drive, front-wheel drive, and rear-wheel drive. So what's something that we learned from these plots? If we go back here to the number of cylinders, we see all the 4-cylinder cars have very little displacement, and the 8-cylinder cars have much greater displacement on their, it's to the right of the displacement axis, and it's lower on the highway miles. Very easy to make comparisons between these 4 cylinder types. Here we've got 4-wheel drive, front-wheel drive, and rear-wheel drive. Wow, that's really interesting. 4-wheel drives span all of the displacements. Front-wheel drives tend to not have very big engine displacements and also tend to be fairly high on highway miles, whereas rear-wheel drives have bigger engines and don't get as good mileage. Finally, we can break it up both ways, drive rows and cylinder columns. At this point, we may have subsetted our data in parts that are too small, but one thing we see right away is that there are no 5-cylinder four-wheel drive cars. There's only a 5-cylinder, a few of them, front-wheel drive cars. The 6-wheel drive cars, there's a whole bunch of those. There's only one front-wheel drive 8-cylinder car. And here's our facet wrap. Okay, I'm going to do it by class. And so we've got 2-seaters up here. Okay, those are all the sports cars. We have the compact cars, get really good gas mileage, and all are just like 4-cylinder cars. They have very little displacement. Here's all your pickup trucks. They have bigger engines and get lousy gas mileage. And so it just starts two-seater, compact, mid-size. It's in alphabetical order, and it just wraps around. And you can specify the number of columns you want before it wraps. Otherwise, it will choose something that makes sense. All right, let's think about how to improve plots. I spend a lot of my time doing this whenever I see someone display information. So here's a plot of the city highway mileage and the highway miles per gallon. And we get this nice positive relationship, as you'd expect. You know, if there was a 1-to-1 line plotted here, which would actually be a pretty good thing to add on this plot, that would indicate whether you do better in the city or highway. Judging by this, this range right here, you get about 15 in the city, 20 on the highway. How about up here? About 30 and 40. So it seems you do quite a bit better, maybe about 30% better on the highway than you do in the city. What's another way we could improve this plot? Well, how many points are there in the data set? Do you remember? Let's go look. So structure of miles per gallon, 234 observations. If we go back to our slide, certainly aren't that many points here. So what's happening? They're being obscured because the resolution of the data are integers at 1 mile increments, 1 mile per gallon increments. So one thing we can do is we can jitter the points. If we allow the points to a little bit of error, add a little bit of noise to them effectively, then they'll lay less on top of each other. Okay? So one thing we observe is that, in fact, in this area in the lower middle part, there's lots of data points, and up in this upper tail, there's many fewer data points. And it seems that we have a really big cluster, particularly in the middle of the data. How did we do that? In the geom point function, we added an argument, position equals jitter. And you can jitter in every direction, that is both in the x and y direction, or you can jitter just in the x or just in the y, and you can determine how much you jitter. And I'll show some more examples of that shortly. So here's another plot. Here we were plotting class along the horizontal axis and highway mileage on the y-axis. How can this plot be improved? Well, the first thing that I see here is my eye follows this. It goes 2-seater, and it sort of increases to mid-size, and it decreases down to pickup, and then it spikes up at subcompact, and then down in SUV. But I'm creating a pattern there that doesn't make any sense. What's the significance or the importance of the ordering of these classes? It's alphabetical. So it has no relationship to what the values of the data are. So one strategy here is to reorder the x-axis. So now we've reordered it, so we go from the lowest mean, pickups as the lowest highway miles per gallon, and in increasing order up to compacts, which have the greatest highway miles per gallon. So there, I put a reorder function in here, and I'm reordering the class variable by the mean highway miles for each class. So reorder is a handy function. I don't use it very often, but it's very nice for this sort of application. What else can we do to improve this plot? Well, we still have the same problem as we had before. Points lie on top of each other. So here I'm jittering the points again. All right. What's an issue, however, with the jitter we've done? I've lost the visual boundaries between these categories. So the jitter, by default, effectively adds horizontal jitter here, and perhaps even vertical jitter. Let's see if we can tell. I think that there's a little bit of vertical jitter as well. Absolutely. Yeah, if we look at this top point up here in the top right hand corner and I go back and forth, you can see how it moves both horizontally and vertically. So one challenge that this has is I've lost the visual distinctions, and it is jittering effectively, as wide as it can without overlapping with the neighboring class along the horizontal axis. So let me go one more slide to the right, and I've reduced the jitter. And so now I get less overlap with my points, but I maintain the visual distinction between classes along the horizontal axis. Now I've had to use a slightly different function to do that. There is a function called geom jitter, and here I've specified as an argument position equals position jitter width equals 0.1. And in this case there is no, I can't compare it to the last one because that one, if we could compare it to 2 before easily, we would find that there is no jitter in the vertical direction. What's something else we could do to this plot to improve it? Well, we still have points laying on top of each other, so we could add a little bit of transparency if we wanted to. And there are several other things we can do. All right, let's see what else. Here is a box plot. So if I go back one slide, I was using jitter for those points, and it's that second line that's going to change to box plot. So I've assigned now a geometric object box plot as what should be plotted. And so we get that plot. This is in increasing order with respect to the mean. You can see the medians here, the central bar of the boxes. It isn't in the order of medians. All right. Here is our first example of layering. So I've created my axes with the first line. The second line, I have plotted the points, jittered. Then I plot the box plots on top of the points, and then I display the plot. So I get the points layered behind the box plots. Let's look at the next slide. I've done two things here. Let's focus at one at a time. The first thing is the reorder that I started with, by default, reorders by the mean. But maybe I want to reorder by the median instead. So that indicates that this subcompact and this midsize, these two here are going to trade places with respect to the median. So if I go forward one, we see that those swap places. The second thing that I've done is for my box plot, I have added transparency by decreasing the alpha to 0.5. Another way to say that is I have decreased the opacity so that you can now see through the box. So the box, instead of being bright white, is now half white, and you can see the points behind. Now maybe what would be even a better strategy rather than making the box transparent? Maybe just bring the points in front. So if we swap these two lines, the jitter and the box plot lines, just put the points on top. So first we put the box plot down, and then we put the points on top. This is a display that I tend to like quite a bit because it gives you all the points so that you show all the data, but also gives you this summary the 5-number summary in the form of the box plot. And you have lots of ways to customize the box plot too. You can specify how wide the boxes are, what color things are, and so on. So this is just the beginning. We're going to do a lot of visualization in this class, and by the end you're going to feel that you have a real command with visualization. My recommendations are to read Edward Tufte's books, or at least go through people's outlines of his ideas on websites. Go ahead and explore visualization online, and do your best to strive for clear, effective visual communication. Your readers will very much appreciate it, and believe it or not, you will think more clearly because of it. Thank you very much.